In this video, we're going to examine Le Chatelier's principle and shifts that are caused by changing the temperature of the system. So first, it's important to understand the difference between temperature and energy. So when we increase the temperature of a reaction, what we're really doing is adding kinetic energy into the system. If we decrease the temperature of a reaction, we are removing kinetic energy from the system. So anytime we play around with temperature, it's always affecting kinetic energy. Within the system itself, so if we imagine our system is some sort of square here, that's our chemical reaction, we have stored potential energy within the bonds. And so when we change the kinetic energy surrounding the system will react to adjust the amount of potential energy that's stored. And so when we shift the temperature with Le Chatelier's principle, that's what we're really looking at, is how do changes that we make in kinetic energy then affect the potential energy within the reaction itself. We're going to look at how increasing temperature in an exothermic reaction can cause stress on an equilibrium system. So we are going to look at the system of nitrogen plus hydrogen in equilibrium with ammonia. This is the Haber-Bosch process. And we see that energy is a term in the products, making this an exothermic reaction. So equilibrium occurs in a closed system, which means that the temperature is constant. The reason that the temperature is constant is that as kinetic energy is either produced or absorbed, it's coming from outside of the system itself, and it's either being released or absorbed from the surroundings. So if we look at this first bar graph at equilibrium, this is the total potential energy of the system. So this is going to be some mixture of our reactants and our product. This is equal to the total kinetic energy of the system. So not only are the forward and reverse reaction rates equal, so is the total energy. As kinetic energy is added intentionally to the system, all of a sudden, the energy of our potential energy and our kinetic energy are no longer equal. And so the reaction is going to shift to convert some of this added kinetic energy back into potential energy. And so we see as the shift or after the shift has occurred, we again have equal energy, but we have more potential energy and less kinetic energy. So what's going to happen in this reaction is a shift away from the energy term when energy is added. In this case, it's going to be a shift towards the side of the reaction with more potential energy. So we add energy, we shift away from our energy term to the side of the reaction with more stored potential energy, so toward our reactants. So this is going to be a shift left toward the reactants. We're going to look again at increasing temperature, but this time for an endothermic reaction. So the reaction we'll look at is the opposite of the last one we looked at. So this is going to be the decomposition of ammonia. So ammonia is in equilibrium with nitrogen and hydrogen, and this is an endothermic reaction because our energy term is on the reactant side of our balanced equation. So with this reaction, once again, we start with equal amounts of potential and kinetic energy in our system. If we add kinetic energy in, all of a sudden we have too much kinetic and not enough potential. And so the reaction is going to shift to meet halfway. So an increase in potential, a decrease in kinetic. The product side of our reaction has more potential energy. And so what's going to happen is the reaction will take some of this added kinetic energy and create more products to convert it into potential energy. So energy is added, we shift away from the energy term toward the side of the reaction with more potential energy. This will be a shift right toward the products. We're going to look now at the effect of decreasing temperature on an exothermic reaction. So we'll study the Haber process again, this time forming ammonia, which is an exothermic process because our energy term is on the product side. So in this reaction, our reactants have more potential energy. So once again, at equilibrium, we have equal amounts of potential and kinetic energy. This time, if we decrease temperature, we're going to be removing kinetic energy. What's going to happen then is our potential energy is going to be the same, but we have less kinetic energy now, and so the two are not equal. So the way to rectify this is to transfer some of our potential energy into kinetic and to kind of meet halfway. And so what's going to happen is we've removed energy from our reaction. So this side of the reaction with more potential energy is going to react more, so it's going to shift back towards that energy term. So we remove energy and then we shift to replace it. Remove and shift. And so this is going to be a shift right towards the products. We're going to look now at the effect of decreasing temperature on an endothermic reaction. So we're going to look at the Haber process again. So we start with ammonia this time, so it's the opposite. We start with ammonia and we produce nitrogen and hydrogen. We know that this is an endothermic reaction because our energy is a term in the reactant side. That means that our products have higher potential energy than our reactants. So once again, at equilibrium, we have equal potential and kinetic energy. By decreasing the temperature, we are removing kinetic energy from the system. And so our equilibrium is going to shift so that we meet halfway. So some of that potential energy is going to turn into kinetic energy. So we're going to see a decrease in potential energy and an increase in kinetic energy. This can be explained because we remove energy. Our products will react to replace the energy that was removed. So energy is removed and products react to form more energy. This would be a shift left toward the reactants. The last thing we're going to talk about is the effect of changing the temperature on the value of KEQ. Changing the temperature is the only way to change KEQ for a reaction. We are going to look again at the Haber process. So we have nitrogen, hydrogen, ammonia in an exothermic reaction. And we have our KEQ expression written. So KEQ is always product, so ammonia squared, over reactants, so nitrogen times hydrogen cubed. So if we increase the temperature of this reaction, we are adding energy. That's going to cause a shift away from the energy term, so a shift left. If we shift left, we are going to increase the concentration of our reactants, so nitrogen and hydrogen, and we are going to decrease the concentration of our products, so ammonia. Our reactants are the denominator in our fraction, in our equilibrium expression. Our products are the numerator. So if we decrease the numerator and increase the denominator, that's going to lead to an overall decrease in the value of KEQ. We can do the same thing for if we decrease the temperature. So if we decrease the temperature, we are removing energy from the system. that's going to cause a shift right to replace the removed energy. A shift right will decrease the concentration of reactants and increase the concentration of products. So once again, reactants are the denominator of our fraction and products are the numerator. So if we increase the numerator and decrease the denominator of a fraction, we're going to increase the overall value, thereby increasing the value of KEQ.